The discovery of radioactive emissions at the end of the 19th century and the early part of the 20th century ushered in a brand new era in human history, an era fraught with possibility and danger. There were immediate consequences. It signaled the existence of a hitherto unsuspected vast energy source. And an immediate consequence of that discovery was that it pushed back the age of the Earth. Now, to put this in context, we should realize that through the end of the 19th century, the best estimates we had for the age of the Earth came from thermodynamics, where, viewing the Earth as an inert cooling body, Lord Kelvin had made calculations which suggested that the Earth should be about 100 million years old. Later calculations downgraded that further to about 50 million years. That sounds like a very vast time period, but part of Kelvin's thinking was that over a period of that magnitude, no known chemical reaction can be kept in place over periods of tens or hundreds of millions of years. And therefore, the proper model would be, apparently, that the Earth was initially formed as a molten body and then gradually inertly cooled in time. Calculations from the heat equations then give us estimates of somewhere between 50 million and 100 million years. This kind of time period is much too short for the evolutionary processes that Charles Darwin's Origin of the Species demanded. With the discovery of radioactivity, all of that changed. Suddenly, a brand new energy source had been discovered, and an energy source which could sustain in a reaction for millions and hundreds of millions of years. And with that discovery, suddenly, we now had tools to argue that the Earth was much older than had been anticipated, and currently our best estimates put the age of the Earth to about 4.5 billion years. And so, quite remarkably, the discovery of radioactive emissions gave strong reinforcement to Darwin's theory of natural selection from a completely unexpected direction. Of course, there were going to be more troubling developments, some acutely troubling and some very promising, but this is going to take some time. Now, here's an experiment which was reported by Rutherford, Geiger and Bateman in 1910. In this experiment, they lightly doped a film of polonium and watched it emit these alpha particles at intervals of 1/8 of a minute for 2,608 successive intervals. And they counted over this entire period 10,097 alpha particles emitted. We immediately recognize an opportunity for a Poisson approximation. What is lambda here? Well, over the entire period of observation, there are 10,097 particles. There are 2,608 intervals, and therefore lambda is the ratio of the two quantities. It's about 4, it's about 3.87. Here are the data reported by Rutherford, Geiger, and Bateman, and we look at the number of intervals where there were no particles emitted, 1 particle, 2 particle, and so on through 15 and more particles. And you observe them in this table. If we compare these with the expected Poisson values, which is take the corresponding Poisson probability of observing so many particles, corresponding to a parameter lambda about 3.87, multiplied by the number of intervals, will give you the expected number of intervals with that many emissions. And even a cursory glance shows remarkable agreement between the observed frequency and the modeling frequency.